Hello.
Yes, sir.
Good morning, everybody.
Good morning, sir.
Very good morning. I'm using a different device this morning and I'm trying to see if it works. I think it is working all right. But I am not able to adjust the screens. Let me see. Hi, Sunil.
Hello, sir.
Very good morning.
Very good morning. Sanjay is not here yet.
Sorry?
Sanjay has not joined yet, or?
I don't see him yet.
Yeah.
I do not see him yet. We have another 8 minutes.
Yeah, sure.
Good morning, Sanjay.
I think he may not be able to unmute yet. Yeah, now he's okay, I think.
Yeah, good morning, Sanjay.
Good morning, Moda.
Yeah, very good morning, Sanjay. We are getting lots of messages from participants appreciating the course.
Oh, great.
Yeah, so I think it's really going very well. It's very helpful for a lot of people. And the kind of questions you are getting suggests that some of our participants are
Involved.
very well read and they are familiar with the field. So I think it's great to have them in the course.
Yeah. I'm only concerned that we are not able to keep the schedule as we have decided. We are a little slow compared to the articles which we have given.
Yeah, that's okay. That is all right. I don't think I will worry about it.
So there's no rush, isn't it?
Yeah, because I don't think it will be helpful to accelerate the pace.
Okay, that's true. That is very much true.
Yeah.
So,
I think
some of the things like that, Bose and condenser, I think I will not be able to discuss if that is the.
Yeah, what we can do, and we can discuss it offline sometime. We can take a little break, and then maybe at your convenience, we can have a follow-up continuation course, which can be 5 lectures, 10 lectures, 15 lectures. Oh, it can have a very flexible format, and it can be done at your convenience. So we will discuss it offline sometime. But the pace is good. I don't think it will help to accelerate.
Good. Thank you.
Because then many students will find it very difficult to cope up. So we will maintain the present pace. So many people are entering the waiting room of this meeting, and I think someone is admitting them. Sunil, is Arijit also with us this morning?
So today he won't be there.
Okay.
Should we start?
Yes, I think so. I was having a little bit of difficulty with my device here, but I think I'm able to. I believe I'm connected. I'm having some difficulty with some of my settings, but I will worry about it. Let me welcome all of you. We are a couple of minutes late this morning. Yes, now I think the settings have come out right. Good. So very hearty welcome to all of you, and very good morning to everybody. Sanjay will continue the lecture. Sunil is with us to help with the session. So Sanjay, you may please continue. Thank you.
Thank you. Thank you very much, Prasanta.
Yeah, Sanjay, maybe I should interrupt you for a moment because that is again the presenter view is appearing on the screen.
Okay, so I have to, yeah.
Yeah, you can disable the presenter view.
Yeah, fine.
Yeah.
I think it's okay. So,
Not yet. Not yet.
not it?
Not yet.
Disable, yeah, disable annotation.
No. Presenter. Maybe you can try to present it again. Last time you had done something to.
Okay, I'll share again.
Yeah, maybe you can try again. Okay, now it is all right.
Is okay?
Yeah.
Okay. So good morning, everyone. So hearty welcome to you for the 5th class. So let us recall what we have done so far. Before that, I would like to remind you that today at 3 p.m. we will have a tutorial. There is a problem sheet shared with you for the second assignment. Okay, please go through them. And what we'll do that we'll share the answers on the screen and discuss them, unlike the last class. Okay, it will be much faster. And if you have questions, so I think you also will ask during that time. Okay, so let us start today's class. So far what we have done, so we have quantized electromagnetic field. Then we have seen that light that vacuum state or zero photon state, okay, which is a non-dispersive kind of state or minimum dispersive state, okay, we can have a state which has number of photons, even large number of photons, but still it behaves like a minimum dispersive state. Then what is showed that, okay, trying to show that there is a mechanism, okay, which actually is used to transform from the vacuum or zero photon state to that particular state which is known as coherent state or quantum coherent state, which is also having the minimum dispersion, and that actually satisfies, okay, the quantum uncertainty relations, okay, where the speed of both the canonically conjugate operator Q and P are minimum and both are square root of h cross by 2. Then we ask the question, okay, which is the mechanism which can transfer from the zero photon state to the coherent state? And we found that there is an operator which is known as displacement operator, which can actually displace the vacuum state or zero photon state to the coherent state. And you can also, if you just do the reverse inverse transformation, you can bring back it to the vacuum state. Then what we tried to explain the last class, okay, details we have discussed that there is a equipment which can be used. Okay, we haven't shown that whether it can be used for displacement or not, but we are trying to show that this is a beam splitter which is in the quantum mechanics framework, okay, that can behave something like mixing of the two lights. Okay, so if you have a, like, let's say that you can think about the quantum lossless beam splitter, which is discussed last class, and which is possible to generate using dielectric layers. And if you consider 50-50 beam splitter, what we showed that if you have an input port, okay, 1 0, then using the beam splitter, you could get output port where you have two detectors. One is a D3 and another is a D4, say. Okay, you will get a distribution, okay, of the photons. Okay, so if you measure them, what would happen? The single photon is the first detector and zero photon is the second detector. What you saw that we can have in the output detector D3 and D4 that sometime we will get the single photon at D3, sometime we will get in the D4. And probability of having them in the two different detector, okay, they will not be having joint because there is one photon was available. So it has to be either in D3 or in D4, okay. So that, but probability of measuring or observing them at the D3 or D4 both are half, okay. So that if you have 100 measurement, you will get 50 times you will measure it, you will be able to measure it in D3, 50 times you will be able to measure it in the D4. Similarly, we showed that the other port, if it is glowed with one photon and keeping the first port will be input ports, just keep it as it is, like vacuum. Okay, so we'll see that other distributions, but probability will be same. And we see that if you have both the input ports are glowed with a single photon, then what would happen that you will get an interesting phenomena that these two detector, so they will not have a single photon jointly. Okay, instead of that, both the photons either it will be go to the D3 or it will be go to the D4. So you will be able to obtain the or will be able to measure them together either in the D3 or in D4, and probability of them is half. Similarly, if you had the two photons together from a particular input port, then you see that you have that all the possibilities. Okay, so you will have that either both the photons are coming to the D4 or both the photons coming into D3, or there will be possibilities of finite probability that jointly you will be able to see that one photon is going to the D3 and at the same time the other photon is going to the D4. So that possibility is there. Then we had said that if you had a coherent light, okay, what would happen? And that is most practical questions, because coherent light, as you have understood that the laser light can be used as a coherent light. So what would see that just like classical case, okay, we'd be expecting that the 50-50 beam splitter will speed that intensity of the light. Okay, half of them will go to the D3 and half of them will go to the D4. Similarly, if you had that, if you have two different coherent light, what you see that the distribution is a little distinct. Okay, so that one port will be getting lesser number of photons, another port will be getting more number of photons. Okay, but number of photon conservation has to be same. Okay, so it will be totally conserved. Okay, so if you just add up, you will get same number of photon as it was in the input port. So if you just see that if you put beta equal to alpha, that means both the ports are actually impinged by the same kind of lasers. Okay, so what we see that you only one port will be glowed, that is the fourth one. Okay, it is as the so this is because of the way we have defined the operator of the beam splitter. Okay, so that's why the fourth one is glowed. And we'll try to see in the experiment whether that is true. So if you have a laser light, okay, which is going through the two input ports and merging in the beam splitter, and what will be the output? So whether both the ports will be glowed or there will be one port will be just as vacuum and no light will be there, and another port will be glowed by both the lights. Okay, we'll see that. One interesting thing which I would like to bring to your notice that if you see that equation 1, where actually you have a one laser light you are shining, and that you are expecting that this laser, okay, it will be distributed between the two ports, output ports, okay, with equal intensity. So this one also you will be able to write in mathematical form that you will be able to distribute in that two port, okay, keeping that total number of photons are, okay, that capital N. Okay, so if you can keep it, this is some mathematical expression, you will be able to see that you have that N number of photon. N can be capital, can go from 0 to infinity, but that N number of photon, whatever number you are summing up, because you have a, you see that you are having here, you are having the coherent state, which is the linear combination of the all number state. A number state can go from the 0 to infinity. So whatever number state you are considering, okay, the particular cases, so depending upon your alpha, suppose you have a lower alpha, okay, that means this will be mostly dominated by the low quantum number or low number states, okay. And for the, let's say that for phi, so alpha is such that up to n equal to 5 is mostly dominated. After that, domination is less. Then you could write each of the number state. Then what would happen that it will be distributed, so that if up to 5 number of photons, okay, so we're just considering n equal to 5, okay, that will be distributed between the 3 and 4. So it will be binomially distributed for each of the cases, okay, for each of the quantum levels that become focus state, okay, will be able to distribute it in terms of the 3 and 4. Okay, so that is mathematically shown. It can be used in many cases. So that's why I just wanted to address it here. Okay, so this is all theoretically we have seen. Let's see that if you have this kind of beam splitter, what is the applications? Okay, before understanding the application, let us just look at some of the elementary things, how we do the quantum interference using Mach-Zehnder kind of interference technique. Okay, so that will be very important, where actually you use two beam splitters. Okay, there is a one beam splitter you see it, another beam splitter you see it here. So this is, I am taking from the YouTube's slides, okay, from T. Bijan's website. Okay, so but nicely described here that how this Mach-Zehnder interferometer works and how it can be used. Okay, so what you see it here, that you have the light, so which actually passes through the aperture. I don't know whether you are able to see this. So the work of the aperture is to that actually make it more focused, okay, so that you will get very little light through that, okay, narrowing down the beam size, okay. And then you have a beam splitter, okay, and you have two mirrors oppositely placed to each other, and another beam splitter is standing here, okay. So one thing you have to make sure in this kind of experiment, that the length between these, from this beam splitter to the mirror and then coming to the beam splitter. Similarly, that another one is that this beam splitter to the other mirror and coming to this beam splitter. These two lengths should be same to get actually the proper physics out of it. Okay, otherwise the light, when they traverse to them, will get extra phase due to the path difference. Okay, so that we have to be at. Now look at the beam splitter. So the beam splitter, as you know, that you are using the dielectric layers. Okay, so it has two faces. Okay, so once, okay, that is a front face. Okay, and there is a back face. What happens that if light comes from the front face and get reflected, you don't get any phase changes. But if it comes to the back face, okay, then if it get reflected, you will get the phase shift. Okay, so that pi phase shift you will get in these cases. Okay, and what you see it now, if the lights, once it comes, let's say that it's coming like here, okay, and coming to the beam splitter, and then what would happen This light, if it goes through, that means transmits through the beam splitter, as the transmission doesn't change the phase, okay, light will pass through this one. And when it comes and hits the mirror and get reflected to get it the other beam splitter, because of the reflection, there is a pi phase shift. Okay, so what would happen that when the light is coming from this path, okay, so light actually, as you understood, as if it is 50-50 beam splitter, half of them will go this way, half of them will be reflected, half of them transmitted, half of them reflected. So that transmitted ones, okay, will when it reaches to the other beam splitter, it already has a pi phase shift. What would happen that when the reflected one, which is coming from the first beam splitter, as I showed that it is from the front side of the beam splitter, which actually doesn't change the phase shift. Okay, so what would happen then when it reflected by this mirror, then you will get a phase shift pi. So when these two beams, which are coming actually originated from the single beam, okay, and that means that we are keeping the coherence of the beam when it is after this splitting, okay, so these two splitted beams are coherent to each other, and when they are approaching or impinging on the another beam splitter, okay, both of them having the pi phase, okay, shift already. And now you see that when they are hitting the beam splitter here in the second one, okay, they will be the green one will hit in the front side, and the red one will be hitting to the back side. So red one, when it hits, what would happen that because of it is hitting in the back side, the reflected one will be having pi shift, pi phase shift. Okay, so that means what would happen that when it comes, that reflected one, okay, which already had pi phase shift, one more pi phase shift will actually nullify total phase shift. So ultimately, upper beam, when it got reflected and coming here, you will get zero phase shift. I believe you have understood this one. Now, what would happen that a transmitted one, since there is no phase shift due to the transmission, since it has already the pi phase shift, it will just pass through and having the pi phase shift here. Whereas that green one, which is coming from the lower path, okay, and that is already having the pi phase shift, when actually is reflected from the front side of the dielectric layer or beam splitter, as you know, that doesn't give any phase shift, so it still gives the original phase shift which was already happened just by reflection from the mirror. So what would happen, both the red light and green light, one is coming from the upper path, one is coming from the lower path, both are having the same phase shift. Whereas the green line, when it transmits, because it has the pi phase shift already, when it transmits to the beam splitter, okay, it will not change the whatever phase shift it had, okay, it will just keeping that phase shift. Okay, that means, sorry, it has that pi phase shift. So what you see ultimately, you see that after going through the second beam splitter, this one, okay, the beam which is coming from the upper path and the beam which is coming from the lower path, they have a phase shift, a pi phase shift, okay, among themselves. And that means this will be destructive, okay. And whereas here, that both the beams, one is coming from the upper path and is coming from the lower path, they will have a similar phase shift, okay, they will have a constructive phase shift. Due to destructive phase shift, which you can see that they will be not having any light there, okay. So that is a black fringe will come. And but what would happen that due to the on phase or in the same phase, okay, they will have a constructive. So what would happen that you will have the full light what was coming here, okay. So what was initially impinged on the first beam splitter will get back this in the particular detector which is in this side. So when you do the experiment, what would happen that you'll only see that you are expected to show that this screen which is lying here will be only glowed, and there's no light will be available in this screen, okay. But in practically, what happened, it is very difficult to align these two paths so that there is no phase shift okay, is created due to the path difference. So if you could make ideal setup where there's no phase shift due to the path difference between this two beam splitter, okay, light when traversing from this upper path and lower path having same path, okay, difference, okay, then what would happen? You are expected. But in practical, it is very difficult. So you will see some light glows here, okay, relatively low intensity, as it is explained in this YouTube channel, and you must see this. Okay, so what you saw that using the two beam splitter and two mirror, this is a novel technique. That what you got that light which was coming got reflected, okay, on the way. So it is you are allowing the light to traverse in a two different paths, okay. And again, what you do, you are merging them with another beam splitter and get back that original light. So that is a novel idea. Like some people who are having the knowledge of particle physics, it's like a pair production. Okay, so you are having the photon, okay, and then you see that that photon actually creates electron-positron pair, and they combine it. Okay, so it's something the analogy I'm just giving. Okay, it may not be practical one. Okay, but this is like similar thing that you are having some kind of a two different paths, okay, allowed by this beam splitter, and then marching it. And now, what is the advantage of that? Now, what you see that this is from the blog YouTube's where he has discussed about the Maxenter type kind of interferometer or the interquantum interference which is can be obtained. So here, what actually one can see that if you have the same setup, so what would happen? So let's try to understand what we saw in Vision's YouTube. Okay, that here actually you have the one path, upper path, and here lower path. Okay, and both the mirrors are sitting here. So the E1 which is actually going through the upper path and E2 is going through the lower path. Okay, now once they merge it in the second beam splitter, what would happen if the second beam splitter also 50-50 as the first beam splitter? What would happen that in the two detectors, okay, you can calculate because of this phase shift due to the path, due to the reflection here and a reflection at the beam splitter, what would happen that here the electric field, okay, will be electric field will be added up. Okay, so we are not doing the intensity adding up. So you have to be careful. The electric field will be added up, and then what would happen? You are just taking the intensity of the combined electric field, okay, which is like that a modulus of E1 plus E2 square. So what you will get that you will get that E1 plus E2 square. And what about in this detector? In this detector, you will get E1 minus E2 square because of the phase shift. Okay. Now, in case if this is 50-50 beam splitter, what we expect that the light which was coming, the field which was coming, it will equally separated, okay, equally distributed between these two paths, then E1 and E2 will be same. In that case, what we expect that this one will be having no photon or the intensity will be zero, whereas this one will be having the intensity which is the original intensity of the light, okay, which was impinged on the first beam splitter. So that is the picture which you see it here. Okay, I hope that you understood that the same thing that what experimental demonstration was shown in the earlier slide, it can be understood in this way. Now, if we just look at that, what is the use of it? As I said that giving an example of the pair production where electron and positron created, and those electron positron can be manipulated, okay, if possible, okay. So similarly here we are also trying to manipulate it. Okay, so what we do? It is a very good one that we are just trying to put one kind of obstruction. It can be any glass sheet, it can be any mica sheet, whatever it is. Okay, some kind of a different density or different effective index medium we are placing on the path. Okay, so what we expect that it will make a phase shift, extra phase shift due to that substance here. Okay, so this extra phase shift when it comes through this lower path, what would happen that it will give the phase. See, the phase shift, since it is phase shift, it doesn't disturb the intensity. Okay, because it comes in the exponential. It is about I delta phi. So the intensity at this point is conserved. There's no conservation of the energy problem. Okay, so what would happen, that only thing that electric field which was passing through this extra substance, okay, will gain some kind of a phase shift, and this phase shift will be able to get it in the detector, like when you just add them up the electric field, so E1 plus E2 by I delta phi E2, and if you just square it up, you will get this one, the intensity coming out from this. And what would happen when you in this detector, what would happen? It will be E1 minus E by I phi E2. So that electric field which is passing through the lower path, okay, it's actually minus sign it will come because of phase shift, as I explained. So it will be E by I phi. So both of the beam, okay, both the detector, okay, will be affected due to that, because now you see that if you do the square of this modulus, okay, amplitude, okay, you will get some effect due to the phi. How? Let us see. Okay, so that you can see mathematically. So instead of having that in terms of the classical field, let me explain it in a quantum mechanical way. So in the quantum mechanical way, as we are explaining, okay, you can think about that these are the two input port, okay, where actually you can have the 0 photon or 1 photon, and you are allowing that these two beam, okay, these two photons, okay, so there's a vacuum here, but it can have some number, okay. These two actually can merge in the beam splitter, and again they split, allowing them to go through the different directions. So if you can start with some alpha here, okay, so that will be like two lasers, okay, as we are discussing, okay. Or you can think about this is a vacuum, this is a single photon, okay, or here it is a one laser, okay. You can think about it. But anyhow, since it's a vacuum and it is a one photon, I expect that this single photon can either pass through the bottom path or can pass through the upper path. Okay, because there are two options it has. Okay, you will have the 100 times experiment, and you will see that this will be 50 times it will be going down path, and 50 times it will be going to upper path. And then again, we are allowing them to to merge it to the other beam splitter. And you are saying that you have a phase shifter here. Okay. And what will be the observation at the C and D detector? So what would happen, as you know that using the first beam splitter, what would happen that you will get the 50-50 probability that it can go to the first path or second path. So that path 1 and path 2. Okay, as this is discussed earlier. Now let us say that that you have introduced the phase shifter. So once you introduce the phase shifter, what would happen? It will just modify this one, the upper path, and so upper path actually, which I'm saying that, sorry, 2. It 1 and 2. So here, it will be I theta 0 1 1 plus I 1. So what you see that you got that phase shift in this case, okay, because of the light passing through this one. Okay. So now what would happen that if you just convert in the C and D port observations, as we have done in the last class, okay, using the beam splitter, again using the second beam splitter, what would happen that you will see that you get that 0 1 will be 0 1 plus I 1 0, and a 1 0 will be transformed like 1 0 plus I 0 1. And but this one will have extra phase shift due to this one. So if you just combine these two, okay, what would happen that you can just combine that 0 1 together and 1 0 together. What we'll see that you will get e by I theta, okay, I theta 0 1 minus sorry, there is something, okay, yeah, 0 1 then there is a, so we have taken I common somewhere, okay, so that you will get minus sign here, okay, and so what will have it by I theta minus 1, and oh sorry, the eye is sitting here. Like, sorry, the eye is sitting here, and these two eye actually will give you the -1 sign. Okay, and the other one, the 1 0. Okay, what would happen that you will get I 0 +1 with additional phase shift I. Okay. Now let us look at that. Now you got that the two ports C and D, and there is a possibility that C port will have 0 photon, and D port will have a D detector. Okay, let's say that call it detector will have 1 photon, and another option is that C detector will get observe that 1 photon, D detector will observe 0 photon. So what is the probability? So if you look at the probability of detecting the photon in different detector, so C detector you can just look at it and you will find that the half 1 plus cos theta. Well, D detector will be half 1 minus cos theta. Okay. So that is the probability, and which actually you can check it. So if there is no phase shifter, if the light is passing through the defined path without any obstruction, any obstacle, okay, what will happen? Theta equal to 0. And then, as it was discussed in the last 2 slides, okay, that what we will see that light will actually, so theta equal to 0 means this cos theta is 1. So you will have a C detector will have full 100% detection of the light, okay, whereas D detector will have a 0% detection. That means there is no hitting in the D detector. Whereas if you make the phase shifter such that the theta equal to 90 degree, then what would happen that because theta equal to 90 degree, okay, so you will have theta, this is 0 and this is 0, cos theta is 0, so you will have a half and half probabilities. Okay. Whereas if you make the theta is 180 degree, okay, you see that the other possibility comes up that you will be seeing that the detection will be there in a D detector full, whereas C detector will not see anything. Okay. So now let us understand it, okay, basically in a single sentence or single derivations. So if we have that 1 photon coming to the first beam splitter, okay, through the port B, and then what you will see that if there is no obstacle, what you will see that you will have 100% heat in the C detector, and the D detector will not have any heat. But let us see that there is an opaque obstacle. So earlier I showed that is a phase shift amount, but there is an opaque. So that means it's not allowing any light to pass through. Okay. In that case, what would happen for the second beam splitter? There will be no light available in this input port, through this input port. Okay. So that means this will be like a vacuum, and the light will be available only through this port. So what would happen? Already that there is a probability that half that due to this beam splitter that this photon will pass through this path. Okay. So that probability of half is already there. So that if you do that 100-time measurement, you will get 50 times that light will pass through that. Other 50 times when it passes through the upper path, that will be stopped. So we are not allowing them, okay, the light to pass through. So that means you are going with from the 100 experiment, we are actually allowing 50 experiment or trial, okay, that light will come to the beam splitter 2. And then what would happen, as it was discussed here in the first beam splitter. So for him, it will be like whenever it comes here, okay, that light, okay, then you will get 1 photon, or whenever it doesn't come, you will get 0 photon. So there will be occasions, there is both of the input port for the beam splitter 2, there is no photon. There will be also occasion, 50% occasion, okay, there will be 1 photon is there from the down part. So now when it happen, then when it will be 0 and 1, again it will be divided half and half. So ultimately what you will see that the C port, okay, will be populated, okay, 1/4 times, and D port will be populated 1/4 times. Okay, that means that 25% times you will see that the C port will be glowed, 25% you will see that D port will be glowed. Okay. So that means that if you have a opaque obstacle, okay, on the way of the one other path, okay, though you are having that 1 photon coming inside, okay, not all the time we will be able to see that photon. Okay, so that 1/4 time we'll be able to see in the C port, 1/4 time you'll be able to see in the D detector. Okay, so on other half, okay, that is other 50%, you will not be able to get any light. Okay, so now what is the importance of this one, this experiment? The importance of this experiment is that so that if there is no obstacle, we will get 100% heat. So we will know that okay, that whatever we are inputting the light, okay, I am getting the output. But if there is any chance that I don't get them, and my system is ideal, like there's no part difference, no other any, let's say whatever we have discussed is like ideal like this one, then if we see that some difference is coming, okay, that means difference means that compared to the 100% heat, okay, that means there is some kind of obstacle here. Okay, either of the path, it will be obstacle. And that one, okay, you can by changing that phase shifter, okay, you can see that okay which path it is there, but it will be there in either of the path. Okay, so what we are seeing that though we are not observing that the phase shifter, okay, we are not detecting them whether there is something is there or not, but by checking the output from the second beam splitter, we are able to say that there is an obstacle on the way. So it's like that without detecting, without doing some kind of pump probe experiment like that, the way we just detect that some we just find out the presence of some particle. We shine the light and we shine another light to get an emission from there and detect it. Okay, so or you can see that the reflected light. Okay, there's some of the techniques by which actually we just detect that some particle is there or not. That we are able to do it without any kind of the conventional technique. Okay, so this is like that though we are not obstructing, though we are not changing anything of the phase shifter, okay, and we are not doing any pump probe kind of experiment, but we are to feel their presence by observing the output from the second beam splitter. So some people say it is a like someone asked in the last class, okay, whether there is a non-locality kind of a phenomena can be observed. Yeah, it's like a non-locality in some case. Okay. So I hope you have able to understand this one. Now let us go to that another application of this beam splitter. So that is one of the application where you can detect if there is an obstacle, or another thing that even if it is not an obstacle, you will be able to say that from the light, okay, output light, what is the phase shifter, how much is actually making the phase shift, and from the phase shift you can calculate that how much density difference actually it was there. So you will be able to tell something about the phase shifter or obstacle. Okay. That is the application of the beam splitter. So now another thing is that what we are saying that okay, then the questions comes that okay, for a long time, okay, when we do the experiment, okay, either we see that okay, we can measure the intensity, or we can feel that there is a variance of the phase from the interference or diffraction features. Okay, so indirectly you can find it. But is it possible to detect them, the phase, directly? So that is the questions which one can ask. Using beam splitter, we will try to see that whether it's possible or not. So this kind of experiment where actually we are trying to observe the phase, okay, that is called Homodyne detections. Okay, and here what we are taking that 50-50 beam splitter, so that's why it is called balanced. 50-50 means the transmission probability is 50 and half, and reflection probability is half. So that means that is called 50-50. And then it is called actually the Homodyne kind of experiment. Now, we can find out the phase of the incoming light, but we need a help. Help is coming from the local oscillator. It's kind of a local coherent light which is very strong. Okay, so that here from this port, okay, so from the first port you are having the signal, okay, and from second port you are having local oscillator, okay, which is kind of a coherent light, but it's strong also. Okay. So both we are allowing both the signal and local oscillator to impinge on the beam splitter to the perpendicular ports, okay, and mix the light. So that is all. And then what we are trying to detect, through the detector 3 and 4, okay, which are actually photodiode, you can think about. So which measure the intensities. Okay. So, so this is like a balanced homodyne kind of experiment, okay. And if I just look at in terms of as we have done it in the last class, okay, is in the second quantized form, which is Heisenberg picture, okay. Then what we saw that in the last class that A3, that output port, whatever the operator you are getting, that can be expressed in terms of the operators which were the input port, the A1 and A2. So A3 will be 1 upon square root of 2, A1 plus IA2. Whereas A4 will be I times, so it will be because of the different reflection phase shift, okay. So it will be 1 upon square root of 2, I A1 plus A2. So if I now combine these two port, output port and detector, what would happen? So here you are obtaining some photon, here you are obtaining some photon. So that these two detections, okay, if we just combine them, taking that whatever signal is coming, so it is photodiode, okay. So that means that when the photon hits it, it creates current, okay. And we are trying to measure this current and bring that current and putting them, combining them. So we can do it two different ways. We can add both the currents or we can subtract them. So if we add both the currents, what we get, okay, that means that number of photons which are coming in third port and number of photons coming in fourth port. Okay, so if we just add them up, so we can write them, okay, number of photons in the third port is A3 dagger A3, that is the number of operator which you can use. And if you just take the expectation value of that, we will get the number of photons in the third port. Okay. Similarly, A4 dagger A4, that will expectation value of that will give the number of photons in the fourth detector. So if we just add these two current, okay, what would happen that you just write back in terms of A1 and A2, and you will see that again you get A1 dagger A1, A2 dagger A2. That means that whatever intensity you had in the first and second port, that is added up. That means that you get the total number of photons which was impinging on the beam splitter from the first and second port. We will get back, okay, once you add the two currents coming out from the two detector. Okay. So that gives the intensity, okay, total intensity of the light, okay, which was impinging on the beam splitter from the first and second port. Now, if I just do that subtraction means that what you can do that you can just A3 dagger in A3, so that is whatever the number of photons impinging on that, and corresponding you will get the current, okay, through that photodiode here, okay. And similarly, you get that A4 dagger A4, which is coming from the fourth port, okay, output port or detector, okay. And if we just write them up in terms of the A1, A2 again, what you will see that interesting thing, you will see that A1 dagger A2 minus A2 dagger A1. So unlike this case when you add it up, where actually you get total number of photons, here actually you will not be able to say anything about the number of photons. It's actually mixed up. So A1 and A2 got mixed up. Now see that, so this is the way we are doing. Now see that what we get from the I minus, okay. So here you remember that from the second port, what we had actually local oscillator, and we say that is like the quasi classical light or coherent light, okay. So it is like a beta t, say, let's say. Beta can be any complex values, okay. Here if it is a strong light, okay, then beta will be very large, okay. So beta t we can write e by I beta times e by I omega t, as you know that from the few classes back, we have explained that, okay. And considering beta is a complex number, which we can write beta equal to beta e by minus I psi. So this is giving you that time variations, and here whatever complex value, we are just writing in terms of the phase, okay. So this is amplitude and the phase is coming. Now let us write it. So, so remember A2 is actually beta now. Okay, so once you replace A2 by beta, what would happen that your I is there, which you can write is the e to the power minus I pi by 2. And from here, in the A2, if you replace by beta, it is exponential I omega t. By beta, you are writing in this form. What you see that this amplitude part of the beta, you can take it out. And what you will get a one dagger that you will have e to the power minus I omega t and e to the power minus I psi. So both will be there for A2. Similarly, for A, the second term, it will be A1 and A2 dagger. A2 dagger that you will have is only that e to the power plus now I omega t, e to the power plus I psi. Okay. So I hope you got this one. Now, once you have this expression, what you see that I just write it, okay, I just absorb the e to the power I pi by 2 inside, okay, and write that psi, modified psi is theta. Okay, so theta, what is that? Psi plus I pi by 2. So not I, so psi plus pi by 2. Okay, then what would happen that I have a1 dagger e to the power I omega t, e to the power I theta. Okay, so because it has gone inside, okay, some of the, maybe we have to check that sign is okay or not. Okay, and then what would happen? I am just writing plus C here. Okay, so I have to just check this. If one has to check this as sign. Okay, so because pi by 2 is there, it will be I pi by 2 is minus or plus 1 depending upon the sign. Okay, so you will get a1 e to the power I omega t e to the power I theta. So I think this is minus I theta. Sorry for this. Okay, so this is minus I theta. This is plus I theta, as you see it from here. Okay, sorry for the spelling, that typo mistake. Now let us see that. Now if I say that signal what is coming from the first port, okay, so say that it is having the same frequency as local oscillator. Okay, so that means it is also can be expressed in terms of the a e to the power I omega t. Okay, and if we just write them, okay, what would happen that e to the power minus I omega t and e to the power plus I omega t. Okay, so depending upon that whether a or a dagger, okay, it will get cancelled. So since it is a1 dagger, so it will be e to the power plus I omega t, it will be cancelled, and here it will be e to the power minus I omega t, cancel this factor. So ultimately, what you see that, sorry, this should be a, not a1. It should be a e to the power I theta plus a e to the power minus I theta. So what we will see that whatever as I said, this is a global phase which you can just forget about. Okay, so whatever is coming out, the current light coming from the port 1, okay, we will be able to write in this format half of a1 a e to the power I theta plus a dagger e to the power I theta. So again, the mistake, minus sign is supposed to be here, plus a e to the power I theta. So the field quadrature operator at the theta, that means we are getting, so that we are writing the x theta, okay, and total I minus then, okay, so half factor is here, so 2 will be coming here. So what will get beta x theta, that expectation values coming from here. So ultimately what we got it, we got the I minus is in terms of some kind of amplitude from the local oscillator, okay, which is known to us, okay, and there is a some quantity which is related to the, okay, the phase, extra phase you have, okay, in that. Now if I set so that by changing the psi of the local oscillator, okay, psi actually is a phase in the local oscillator as you see it here, okay, by changing the psi, what you can change that theta value, so because theta is psi plus pi by 2. So if I just modify the psi and such that the theta equal to 0, what you will see that x theta is nothing but a plus a dagger by 2. Okay. And you know the beta part. So whatever the I minus that current you will get, okay, that actually you are transferring in terms of the creation annihilation operator, and what you will get, you can write it in terms of a plus a dagger of the light which is coming in the first port, through the first port. So what does it mean? It means that it gives the amplitude. So it is, since it is the complex quantities, okay, it gives the amplitude of the signal. Whereas if you put that psi such that psi is 0, okay, so that theta equal to pi by 2, okay, then what you will see that is a minus a dagger by 2. So that from here, what you can find out, this is nothing but the phase of this signal which was coming from the through the port 1. So by comparing these values, okay, so by measuring, so you have to just take the ratio in the measurement experiment measurement, you just take the ratio of I minus by I plus, okay, by changing the phases of the local oscillator, okay, you sometimes you will get amplitude of the signal, or sometimes you will get the phase of the signal. So this is the way you can directly measure amplitude and phase, not like the indirect feeling that there is some kind of interference is happening and you will get the fringe patterns. Okay. So this is a direct measurement of the phase. So, and that is only possible, okay, if you have the beam splitter and you are using this kind of technique like a Homodyne experiment where you are measuring the phase. Okay. I believe you have understood, okay, this one, or you can go through that Jerry and Knight books or Fox books also for a supplementary of this. Okay. So far we have used a balanced kind of beam splitter. Let's see that another use of the beam splitter where actually it is unbalanced. Unbalanced means that the reflection and transmission coefficients are not same. Okay, that means probability of the transmission and reflection are different. And let's consider that probability is 99% for the transmission, okay, and 1% for the reflection. That means that whatever the signal is coming, okay, we are allowing the signal to be observed in the third port, okay, or third detector, okay, as most as whole. Okay, so what we say that we just try to see that light is as much as possible what was impinged coming to the third detector. But there is a local oscillator, okay, which actually plays a role here, as we have seen now, just now. Okay, so what it does, actually, what we have that we have is local oscillator which is very, very strong. Okay. Now, if you use that, because that transmission probability is very high, you will get that the local oscillator light mostly here, okay, in the fourth port. But because of this, the presence of this two, what would happen? There will be some interesting thing will happen. Let's see what is the interesting things. Okay. Now, what you see in the so we have to observe in the third port what is going on. So when you have a strong local oscillator like local quasi-classical coherent light, okay. So what you know that for coherent light it is a eigenstate of the annihilation operator. So A2 operating on beta, you get beta beta. Okay, so beta is any complex value. Here, if it is strong, then beta value is very large. Okay, then what we can see that if you take the expectation value of the number operator, okay, you will get the intensity of the beta of the local oscillator. Since the transmission is very high, what you expect that photon in the third port, okay, will get most part of the whatever light is coming from the first port. Okay. Now, so what we can write that A3, okay, whatever is we will be able to observe is transmitted from the first one, that TA1, and reflected from the second one, okay, and so it has a minus sign and R, okay, reflection coefficient, whatever small amount it has coming from the local oscillator, okay, so that is A1, sorry, A2. And then what would happen that using that R square plus T square equal to 1, what we can write that R we can replace by square root of 1 plus T square. And you remember T is very large. Now, if I just take the T common, okay, or T I can set, T I can just take a common from the both the terms. Okay, what would happen that I will have a T common, I will have A1. So I just take the expectation value of A3, okay, then it will be T of A1 minus, okay, again what would happen, sorry, here what would happen that I will have a expectation value of for the A2, okay, I'll tell what is A2 happening, so just wait it. Okay, now what is happening here, you take T common, and since T value is almost 1, this will be unaltered because this is very, very small quantity, and the small quantity will be almost unaltered. Okay, and what would happen, that beta we are writing in place of the A2. Why is so? That is because, so A2, as you remember, is very strong. And when you have a strong coherent light, as we explained earlier also, okay, that will be dominated by the higher energy levels of the photon number. Okay, so that it will be mostly dominated by those higher levels. They are actually n and n plus 1, doesn't matter. Okay, so which level you are talking. So in that case, what we can consider that the coherent light also eigenstate of the creation operator. Okay, so what would happen that now here we don't need record that here actually what is happening that here because of the A1 we are getting A1 expectation value here A2. Okay, because A2 for A2 beta is giving you beta, so you are getting beta here. Okay, so ultimately using the expectation value, okay, what you got it at Ta minus square root of 1 minus t square beta. Now, what does it mean? In terms of the operator, it looks like that A3 is nothing but Ta1 minus square root of 1 minus t square beta. Okay, so this is the one of the great things which we have to just pay attention. So we are able to get when it is a local oscillator strong and when we have the light which is coming to the beam splitter, which is almost 99% transmission probability having. Okay, then what will have that A3 in the third port for the signal, whatever is coming is almost coming the same signal coming, and there will be small modification by the other or local oscillator which is reflected from here. So now, so from this side, what you see that this is like the operator which we have used in the case of displacement operator. If you do that A1 by displacement operator of amount of square root of 1 minus t square beta, what do you see that you get the right hand side of this one. That was the identity which you have proved in the last class also. Okay, so if you have d alpha A1 d dagger of alpha, you will see that you will get A1 minus alpha. Okay, so that this feature, okay, will show that whatever we will get in A3 is nothing but the displacement of A1. So using this beam splitter, which is unbalanced and unbalanced in such a way that transmission probability is very high, what you could get that you could displace that A1 to some quantity which actually, okay, you can observe or detect in the third port. So output of the third port is equivalent to that what you can say that a displaced signal coming in the first port. Okay, by amount of the displacement is the square root of 1 minus t square beta. So let me stop it here. So that this is one of the application which we have told. Now, thing is that in the next class, okay, now we will start the squeeze state. So I believe that you have understood that application of the beam splitter in the last 3 examples. Okay. So if you have any questions, you can ask it. One small thing which actually I was fumbling in the last class, okay, since I don't do the arithmetic properly. So when you are talking about that particular superposition of a 0 and 1 state of particular coefficient, I was right in the slides, okay. So what happened that when you take the dispersion relation, okay, you get that Q dispersion, okay, that is standard deviation or variance of the Q, okay, what you can see that is 3 by 4 minus 3 by 8. Actually, this is 3 by 8, okay, so this is a half of this one. So that 3 by 8 is less than half. So that means this one, okay, that for this kind of a state, okay, which is superposed between the 0 photon and 1 photon, okay, can be having that that dispersion, okay, in the Q quadrature is squeezed and P quadrature will be amplified. Okay, so what was written in that last slide was right. Okay. With that, I'd like to end today's session. So I'd like to have some questions from the whatever we have discussed at the application of the beam splitter. Thank you for your attention.
Thank you, Sanjay. I think one alert student in yesterday's class did point out that the equation was actually correct. And
right. This is my student only. Tiny has pointed out.
Yeah, there was a remark. There was a remark in the chat box, and somebody was alert and
but
checked it out very quickly. So anyhow, I think Sunil will conduct the question answer session. Sunil?
Yes. So there is okay. There is one question. Can we have half photon? Can we have a half photon?
Half photon. So I
This is a
think
question from Asit.
so yeah. So photon you can't split it, isn't it? So there's no question of it is a fundamental particle. Okay, having the spin 1. Okay, so it doesn't have any structure. Okay, so if you have to make it half, then you have to have a structure of this. So that is difficult. That is not possible. Okay, to the knowledge which we have.
Okay. Then there is a next question. How is the phase shift measured? Is that possible in experiments?
Yeah. So as I showed in this example here, okay. So when you just do the detection here, okay. So when you do the detection, you will see that your get the intensity in the two detectors, okay, will be different now. Okay, because let's take an example. Okay, so if that delta phi is 0, then what we will have that this one will be that U1 plus E2. That means you will get that same intensity as it was in the initial beam splitter. Okay, and this detector will not have anything. But if, as I showed in that, if there is some kind of a theta if you think that this is 90 degree, okay, the delta phi is 90 degree, what would happen that then what would happen? This you will get as we have explained in that second slide, in the probability distribution, okay, that the detection in the C detector, okay, let me put it as full screen. So C detector, okay, what would happen? You'll get that full, C detector, you'll get half of the probability that in the C detector, half of the probability in the D detector. That means that half of the times, okay, that single photon which is coming will hit in that, half of the time it will hit in that. So what would happen from by observing this detection, okay, or observation in the detector C and D, you'll be able to infer that whether there's a phase. Okay, and amount of phase you will be also able to say that by changing value of theta. So if you consider that in the classical kind of example, where if you have a laser light, okay, you are shining it through this, then as it was explained in the last slide, okay, that by using the addition of the amplitude, okay, and subtraction of the amplitude, okay, due to this phase shift, whatever amount, okay, there is a change in the intensity of the detector A, C and D. From that the detection, okay, the intensity variation, you will be able to say, or you will be able to extract, okay, how much was the phase shift happened on the way. I believe it answered to your question.
Okay. So now Abhijit Kundu has a question. Is there any difference between quantum beam splitter and classical beam splitter that we use in a lab?
Yeah. So
means which are okay. So
yeah.
in lab,
so in the lab we don't have. So here there's a very good question. Okay. So we are doing all those things, but using what is that? Is there in the lab? Lab actually we don't have the quantum beam splitter. We are using a classical beam splitter, but the source of light, those are quantum, the quantized light. Okay, you are having single photon, two photon. So if you are using that different quantized light, okay, and allowing that to pass to the classical beam splitter, where the classical beam splitter behaves whatever we have explained, that the operator, it behaves like that same operator. Okay. So still you are using the classical beam splitter. There's no way we can make, or experimentally you can make, in the sense that you can use some kind of a atomic systems, okay, which you have to understand as a beam splitter, okay, or some kind of optical fiber which you can make with the impurity as a beam splitter. Those are possible, but those you will not be able to directly detect. Okay, like here. Okay, you have to do some experiment and indirect way. You have to understand those are the beam splitter.
So,
I don't know whether you followed it or should I repeat it. Maybe you can. So did you
okay.
follow that?
Yeah, if it was not, if it was not clear, you can write. Yeah, more questions. Okay, so there is a question from Pralay Biswas. Is it possible to create one photon at a time experimentally?
A single photon.
Single photon experiment.
Right. So that's always possible. Now it is very much possible. You can have a single photon source. Okay. So there are the techniques available. Okay. So you can have a single photon, two photon. Those are possible. But if you don't have, because those are very sophisticated techniques, the way you can have the quantized light, just for your knowledge, I'm saying that you narrow down the aperture. If you narrow down the aperture as much as possible of the laser, okay, like the one which I showed in the T Vajan's experiment, okay, there's an aperture was used. So that means if your aperture is very, very narrow, okay, you are allowing very few number of photons to pass through. If you can think about that in a particular laser light which is having 10 number of photons, okay. Now, if you just make very, very narrow, much narrower than some micro size of the aperture, okay, then you will have at least maybe 1,000 photons or 500 photons can be allowed, okay. So you can narrowing the aperture and make it as a coherent source of light. So that is another simple way to understand.
Okay. So there is a question from Bharat. What happens if we pass a single photon through a beam splitter, since we cannot have a half photon?
Yeah. So whatever actually explanation which you have given, okay. So I think I don't know whether you followed it. We have only single photon here. If you see this slide, okay, we have the single photon coming through the B port, okay, and there is no photon coming from the A port. So that when the single photon comes using the in the beam splitter, because beam splitter is 50-50, means 50% transmission and 50% reflection. What would happen that in particular trial event, okay, you get either the photon going to the lower path or other trial you will get in the upper path. So if you just detect them, okay, if you put a screen here, okay, and you just think about it, you are sending a marble ball, okay, to the beam splitter, okay, and trying to detect in the one of the screens, suppose, which is standing here, okay. So what you will see that if the 50-50 beam splitter, half of the time you will be able to see the marble, half of the time you will not be able to see that. Means half of the time that marble will hit through a screen, and half of the time actually you will not be able to see. So that means that the other half will go to the other part. Okay. So if you can put another screen here, you will see that when the photon is hitting here, you will not get the same hitting because you have to keep the time observations. Okay. So when the photon is hitting in the this or marble unit is hitting in the this screen, okay, it will not hit in this screen here. Okay. So it will be alternative way, or sometimes here, some 4 times it will be hitting here, 4 times it will be hitting there. Okay, so that random way, okay. But if you take a statistical average, it will be half of the times it will be hitting in this skin, which is standing on the lower path. Half of the time will be hitting in the this skin, which is standing on the upper part. Okay, so that is the way we do experiment. We have to do a statistical measurement. Okay, so experiment is a statistical. Okay, that you have to understand in quantum physics.
Yeah, Sanjay, I am reminded of Feynman's remark here, which he makes in his one of his lectures, that the Young's double slit experiment contains all the essence of quantum mechanics. So when you perform a measurement, you find which way the photon has gone. But till you perform the measurement, it has both the possibilities contained in it. Right. So that is what you're seeing in this phenomenon as well.
Okay. So now Yaksha has a question. In the beam splitter, we when we insert an obstacle in the path of one of the beams, you said that we are able to detect the obstacle without interaction. But for the photons are actually interacting with the obstacle. It is this interaction that prevents them from passing through.
Very good.
Can you please explain this interaction part again?
So actually, what I meant to say that in that when you have any obstacle, whatever happened that you realize the obstacle by sending another signal, okay, to the obstacle and get it back. Okay, it's like you can think about a mirror. Okay, so you are shining a torch on this. Okay, and you are seeing the light in the reflected image. Okay, so you need some kind of light. Okay, to see that that whether that obstacle is there or not. Okay, here what you do that you are observing that reflected one. Okay, and saying that okay the obstacle is there. But here what you see that we are not actually observing this this light which is going through that obstacle. We are just measuring the light which is away from the obstacle. Okay, so that's why it is called non-locality. In the sense what we say that we are measuring the light which is away from the obstacle, which is not actually interacting with the light at all. So that is the information which you gave. The light which is obstructed, okay, by this phase shifter, okay, we are not measuring that. We are measuring that other light. From the other light, we are actually able to see. Okay. So that is the meaning of that. What I have to say that no non-locality, that the lights actually which we are detecting can be used, okay, to say that what is the phase shifter, whether it is there or not. So here actually you have to, for that actually we are only can say whether it is there or not. If you want to know how much phase shift is there, for that you have to observe both of them. Okay, so that is a distinction. So if there's something is there, for that if you just say that there's a totally block, if you can block it and see it, okay, that both the parts is there, something is there. Okay, as I said that if you does no nothing was there, no phase shifter was there, you will get only one detector glowed by the photon. Other detector will not get anything. So anything deviation from that, keeping that setup as it is, okay. If anything deviation from that means that only C photon will be glowed, and D photon will not be glowed at all. So that's actually give you hints that there is on the way something is there. Okay. Now here in the non-locality things when you are talking about, there actually we are using totally opaque obstacle, so that the light is not passing through the obstacle, and we are inferring the presence of the obstacle by observing the other light which is not actually interacted with the obstacle at all. So you see that the other light which is coming through the lower path didn't interact with the obstacle. Yeah. It is actually that the one which was just stopped there, that is interacted. Okay. So the way we actually able to infer here, okay, with the light which was not actually faced to the obstacle. Okay. So that's why we are saying there is non-locality. I hope you got it, what actually it meant it. If you have understood this, please let me know. Yes or no.
Yeah, actually there is a question which may not be really relevant, but I will just say it. Asit, for a theory course, how do I clean the glass in my beam splitter? How do I clean the glass in my beam splitter? I think this is
how do I
clean the glass?
Oh, in the okay, in the beam splitter or?
Yeah, in the beam splitter.
So there is solutions available. Okay, there are solutions available. You can just put it and using some. There are nowadays very good techniques are available. Okay, you can wipe it out also. So those are available. So you can just look at it website. It is there. Okay, so that is very common nowadays.
So Girish has a question. How can we reduce losses that happen during the experiment so that we can get a correct number of protons?
Okay. So, so here what happened that you will not be able to Means for that, okay, my question was very relevant in the sense that since we are talking about few number of photons, okay, so you have to make that corrections, okay. So that here what happened that if you lose photons, okay, by any means, in general it is very difficult, okay, but there is something called error corrections, okay. So using a technique, theoretically I will be able to tell, okay, but experimentally at present I don't have knowledge, okay, for that. So for that, okay, you have to take a help of the other state, okay. So there is something called quantum error correction, okay. So I don't know. So what you have to do that you have to use a supplementary state, okay, and perform the experiment there also, okay. And at the end, what you do, you take the partial test with respect to the supplementary one, and get the actual one. Okay, so maybe we can hold it once we have that discussion on quantum computation and quantum information. If we have, then we'll be able to discuss this one. It's which is called quantum error correction. A very good questions.
Yeah, there are two more questions, but once again, this is mostly experimental.
Yeah.
How do you build a beam splitter to home?
How they build a beam splitter? Okay. So there are different techniques available. Okay. In intuitive way, I can say that. So generally, you just have a dielectric layers. Okay. So you have a glass plate. Okay. Coat a dielectric layer on it. Okay. And it will have some different refractive index compared to the glass. Okay. And by changing the thickness of the coating, you can change the transmission coefficient, reflection coefficient. Okay, so that is the way actually you can make the beam splitter.
Okay. Finally, one more question. Does a photon ever die? Does a photon die?
Oh, does a photon die?
Yes.
So as you saw that, okay. So to die a photon means that either it has to be absorbed by some element, okay, or it has to scatter. It is not dying. Absorbing is the only way to make the photon die, okay, by some atom or some matter, okay, which it can absorb the photon. That way it can die. Definitely.
Okay, so I think with that, all the questions are complete. So I think now we can conclude the session.
Yes.
Thank you.
Yes.
Very interesting.
Okay. Yeah. Thank you, Sanjay, for.
So next class we'll have a quiz state. That
Yeah.
is a Monday, and
Okay.
today afternoon 3 o'clock we'll have a tutorial.
Yeah. So the tutorial, the problem set is already uploaded in the same folder, which was shared with everyone earlier.
Yeah.
So they can.
So I
get
would
it from
advise that you should actually little bit try those problems. Even if you couldn't complete, actually, if you have tried, then you will have some kind of a understanding, okay, and you have a good knowledge, okay. Though that this will be discussed in that tutorial.
Yeah. Okay. Yeah. Thank you very much for patiently answering all the questions. And now also thanks to all the student volunteers who were willing to pass the questions to the Sanjoy. Also the IT technical people, so they were always there for any kind of support whenever needed. And of course, all the participants who were really patiently listening to the lecture, so and asking so many questions, making it very interactive. So I think with that I would like to conclude, and we can now stop the section, end the section for today.
Thank you, Sunil. Thank you for everyone.
Yeah, thank you.
Thank you, Sunil, and goodbye, everybody.
Goodbye.
Goodbye.
Yeah.
Yeah.
Okay. Goodbye.
Goodbye.